But anyway, today we are continuing our conversation. We're continuing section 4.1, and we'll probably dabble a little bit in a 4.2. 4.1 and 4.2 are like the same things. 4.2 is just like a slightly advanced 4.1. But anyway, I just put these section numbers here for your convenience, although I hate them because math does not break down in convenient little sections. It's just one giant blob of awesomeness. So it's hard to tell when one part ends and another begins. There is no really beginning and end of subjects. They all kind of blend together. And so, yeah, but anyway, the real thing we're doing today is talking about mathematical proofs. We did our second proof last time, proving that the square of any odd number is odd. And before that, we proved that adding any two evens together will give you an even number. So we've done two proofs so far. And I have, how many do we have today? We have 1, 2, 3, 4, 5, 6. We have 7 possible proofs today. We'll see which ones we do, how far we get. But anyway, let's just start out by reminding ourselves what we're doing. So really, every statement we can make, or I should say every quantified statement is either a universal statement, otherwise known as a for all statement, or is an existential statement, otherwise known as there exists statement, or like a there exists, something like that, right? Even the ones that look weird, like even the ones that look like, hey, for all x and d, there exists a y and c such that like p of x, y. Even this is really just a for all statement where the predicate happens to be a statement that's a there exists statement under the hood. But it really is a for all statement, right? And no matter what we do, I mean, like we only really showed examples in class with two quantifiers, but there's no reason you couldn't have a for all x and z, there exists a y and the real numbers such that for all c and the rational numbers, blah, blah, something happens, right? There's no reason you couldn't have that. And this statement would be a for all statement. Just the first one kind of dictates what you're saying. You're saying for all x in the integers, something happens. So it's a for all statement. So we have for all or there exists statements. So, and then every statement in math, theoretically, is going to be true or false. Now, I say theoretically for some very, very interesting reasons that I hope we'll talk about, like the very last day. We're going to have a fun class where we talk about all the math theory and all this high-level stuff I think is fun. But every statement in math is either, just the way you can think about it now is that every statement in math is either true or false. There are some very particular statements that are actually neither true or false, depending how you look at it, but they're definitely not going to be both. So the point is, you're either going to try to disprove or prove something. And so to prove, let's do existential first. Or let's do universal first. Universal statement. So to prove a universal statement, we must show that to prove a universal statement, such as for all x and d, p of x, right? Because all universal statements really have this form no matter what p of x is. To prove a universal statement like this, must show that p of x is true for any x and d you plug in. Who's got, and then what's one way we did that?
For finite domains, you can use the method of exhaustion.
Exactly, Sava. Because could not have said it better myself. So one option to try to prove this is method of exhaustion. So I'll say proof methods. We had method of exhaustion. And this works for finite domains. So theoretically, for finite domains, you could always use method of exhaustion if you had enough time, right? We've been over that before. Another method is called direct proof. Let's just get right to it, right? No reason to beat around the bush with this proof. Direct proof. And that's the method that we used in the last two classes to prove that the sum of any two even numbers is even, and to prove that every odd number squared is odd. And direct proof, it always goes like this. It always has this form. So if we're trying to prove for all x and d, p of x is true, for direct proof, what you do is you let x be an arbitrary but particular elements of D. Then show that the property of x and d, or maybe I should then argue that the property of x and d logically leads to x having the property that p of x is true. So we've kind of been over this before. This is called direct proof. So what you do is you let x be an arbitrary but particular element of D, then argue that the property of x and D logically leads that the property leads to x having the property that p of x is true, right? Then if p of x is true for any x in D, p of x is true for every x in D. Proof done. And that last line is a kind of subtle distinction, right? But the idea is we're going to let x be any arbitrary but particular element of D. Now, what we mean by arbitrary but particular, what arbitrary means, arbitrary, that just means that it's just any old element in D. We can't assume anything about it. So for example, in our odd number proof, right, where we prove that the square of any odd number is also odd, we couldn't assume, we started that off by saying like, let n be a particular but arbitrary odd number. But we couldn't assume anything else about it. We couldn't assume that this odd number, n was a prime. We couldn't assume it was a multiple of 3, even though some odd numbers are prime and some odd numbers are multiples of 3. But the point is it's arbitrary. So since not every odd number is a prime, and since not every odd number is a multiple of 3, we can't assume anything about it. It's just any old bland odd number, nothing special about it. That's what arbitrary means. Particular means that it's a particular one. That even though it's any old bland number, we don't know anything about it, it is one number. So we can't kind of switch back and forth and say like, oh, it's even now and then it's odd or something like that. It's one particular number, but it's an arbitrary number. We still don't know anything about it. And this will make more sense as we do more examples. And then we argue So we pick this arbitrary particular x and d, and then we argue that the property of x and d logically leads to x having the property that p of x is true. And I use the word argue here. I changed it from a show to argue because we really are doing like an argument. Like remember we had arguments, we had like the modus ponens, modus tollens, we're doing that. We really are kind of doing those kind of arguments, except we're not going to point them out. We're not going to label them. We could, but we're not going to make everything easier to read and stuff. But we really are doing arguments. Like every logical step you take, like saying like this leads to this, should in your mind kind of be supported by some argument. For example, like if you know that this particular number x is either even, if you know that x is even or odd, and you know x is not odd, well then x has to be even, right? And that's by elimination, right? That's that you can make that logical step because we know there's an argument that supports it. Things like that. And then anyway, this last step right here is subtle. So once you've proven that for any x in the domain, p of x is true, well, if it works for any of them, it's got to work for all of them, right? Does that make sense? Like if any Virginia Tech Hokies player is a beast, that means every Virginia Tech Hokie player is a beast. You can't find a single one that's not a beast. That's a true statement. So, any questions about this? Then let's do an example. Cool. Actually, before we do an example, let's finish this conversation right here. So I was saying that either universal statement or the existential statement, right? Universal statement to prove true, we need to prove it worked for all of them, and we can do that by method of exhaustion or direct proof, which we'll do in a second. To prove false or to disprove, how do you disprove an existential statement?
Find a counterexample.
Find a counterexample. So to disprove for all x and d, p of x, find an x and d such that not p of x. That's all. And I've kind of been treating this as different things. Like I kind of been treating like proving universal statement, disproving universal statement, proving existential, disproving existential. They're really the same thing, right? Because when we're disproving something is the same thing. Disproving is same as proving the negation. Right? If you're saying something's false, something's not true, that means its negation is true. So disproving for all x and d p of x is the same as proving the negation of this, which is an existential statement. There exists an x and d such that not p of x, right? And how do you prove an existential statement?
Find one example where it works.
Find one example where it works, right? So that's why we have this relationship between disproving universal statements is the same as proving existential statements. Because disproving universal statement is proving its negation, which is an existential statement. So yeah, so disprove, you find a counterexample because that proves the negation. Make sense? All right.